Okay, all right, let's just get into it though. So we have an introductory example to Chapter 2, Computer Models and Aircraft Design. To design the next generation of commercial and military aircraft, Boeing's Phantom Works used 3D modeling and CFD. They study the airflow around a virtual airplane to answer important design questions before physical models are created. This has drastically reduced design cycle times and cost, and linear algebra plays a crucial role in the process. The virtual airplane begins as a mathematical wireframe model that exists only in computer memory. This model organizes and influences each step of the design and manufacture of the airplane, exterior and interior. The CFD analysis concerns the exterior surface. Although the finished skin of a plane may seem smooth, the geometry of the surface is complicated. In addition to wings and a fuselage, an aircraft has nacelles, stabilizers, slats, flaps, and ailerons. The way air flows around these structures determines how the plane moves through the sky. Dude, building a plane has got to be a no joke. But honestly, in some ways, I feel like now building a plane and building a car, both are crazy hard. Um, Equations to describe the airflow are complicated, and they must account for engine intake, engine exhaust, and the wakes left by the wings of the plane. To study airflow, engineers need a highly refined description of the plane's surface. A computer creates a model of the surface by first superimposing a three-dimensional grid of boxes onto the original wireframe model. Boxes in this grid lie either completely inside or completely outside of the plane, or they intersect the surface of the plane. The computer selects the boxes that intersect the surface and subdivides them, retaining only the smaller boxes that still intersect the surface. The subdividing process is repeated until the grid is extremely fine. A typical grid can include more than 400,000 boxes. The process for finding the airflow around the plane involves repeatedly solving a system of linear equations that may involve up to 2 million equations and variables. That's pretty insane, yeah. The vector B changes each time based on data from the grid and solutions of the previous equations. Using the fastest computers commercially, the Phantom Works team can spend from a few hours to several days setting up and solving a single airflow problem. After the team analyzes the solution, they make small changes to the airplane surface and then begin the whole process again. Thousands of runs may be required. Okay, so this chapter presents two important concepts that assist in the solution of such massive systems of equations. Partitioned matrices. A typical CFD system of equations has a sparse coefficient matrix with mostly zero entries. I'm loud. Let me get a little low. Get low. Okay, so a typical CFD system of equations has a sparse coefficient matrix with mostly zero entries. Grouping the variables correctly leads to a partitioned matrix with many zero blocks. Section 2.4 introduces such matrices is partition. I honestly don't know anything about that, so that'll be interesting to learn about. Introduce such matrix and describe some of their applications. Matrix factorizations. I kind of know about matrix factorization, but not really. So this is what I'm actually really excited to learn about this. Matrix factorizations. Even when written with partition matrices, the system of equations is complicated. To further simplify computations, the CFD software at Boeing uses what is called an LU factorization for the coefficient matrix. Section 2.5 discusses LU and other matrix factorizations. Further details on factorizations will appear at several points. Yeah, because this is where you start getting into actual. Dude, look at that plane. Holy cow. That would be crazy. Imagine flying in that thing. That would be wild, dude. Imagine flying in a plane like that. To analyze a solution of an airflow system, engineers want to visualize the airflow over the surface of the plane. They use computer graphics, and linear algebra provides an engine for the graphics. The wireframe model of the plane's surface is stored as data in many matrices. Once the image has been rendered on a computer screen, engineers can change its scale, zoom in or out of small regions, and rotate the image to see parts that may be hidden from view. Each of these operations is accomplished by matrix multiplications. Okay, so we're about to get into the real stuff. Our ability to analyze and solve equations will be greatly enhanced when we can perform algebraic operations with matrices. Furthermore, the definitions and theorems in this chapter provide some of the basic tools for handling the many applications of linear algebra that involve two or more matrices. For n by n matrices, the invertible matrix theorem ties together most of the concepts treated earlier in the text. Section 2.4 and 2.5 examine partitioned and factorizations, which appear in most modern uses of linear algebra. 2.6 and 2.7 describe two interesting applications of matrix algebra, economics and computer graphics. And 2.8 and 2.9 provide readers enough information about subspaces to move directly into chapters 5, 6, and 7 without covering chapter 4. You may want to omit these two sections if you plan to cover chapter 4, but moving on to... Oh, really? Okay, let's get into it, bro. All right. Matrix operations. If A is an m by n matrix, that is, a matrix with m rows and n columns, then the scalar entry of the ith row and jth column is denoted by aij and called the ij entry of A. See figure 1. For instance, 3, 2. Is that actually true in Python? What? Can I just index it like this? Wait, what? Oh. Oh, wait, you know why? Because it's 0 index. This should be 1, 0. Okay, great. So it's still okay. So the indexing of NumPy is still like this. I think it's how it's stored in memory. I think it's that it's stored row wise in memory, and that would be indicated by this. But it's still indexed with columns first, or with rows first. Wait. So the contiguous would be the contiguous. It'd be this, then the next row. All right. Okay, that's column. Observe that. Okay, the diagonal entries are okay from the main diagonal. A diagonal matrix is a square matrix whose non-diagonal entries are 0. Okay. An example is the identity matrix whose entries are all 0 is a 0 matrix. Okay, that's great. Okay, here's indexing. Sums and scalar multiples. The arithmetic for vectors described earlier has a natural extension to matrices. We say that two matrices are equal if they're the same size and if their corresponding columns are equal, which amounts to saying their corresponding entries are equal. If A and B are matrices of the same size, then the sum is just the column sums. I mean, yeah, just you do the basic thing. Since vector addition of the columns is done entry wise, each entry in A plus B is the sum of corresponding entries in A and B. The sum A plus B is defined only when A and B have the same size. Cool. Okay, scalar multiple of Okay, so we have commutativity, we have associativity, we have a zero element. Interestingly, they don't say that there is a they don't say that there's an inverse, interestingly, but there must be an inverse. Because I think if we look up module, yeah, see, M over plus is an abelian group. And then you just get yeah. So okay, well we'll get into it later, but let's just write down theorem 1. So A, B, C matrices of the same size. Then we have A plus is a soak, com, and we have a 0. Okay, then so this is A, B, and C. It's interesting that they leave out the inverse element, right? Okay. They call this distributivity, right? Yeah. So in a what is this one? What is that one called? Is that just in the definition of a ring? Oh, okay. So this is called left distrib, and this is going to be B or R plus S times A equal to RA plus SA, and this is right distributive. Okay, what else do we have? Then lastly, we have associativity. Where is that one? What is that called? And then we have I think it's just associativity. Each equality in Theorem 1 is verified by showing that the matrix on the left side has the same size and the corresponding columns are equal. It's weird that they always go column-wise, but anyways, size is no problem because they're equal in size. The equality of columns follows immediately from analogous properties of vectors. That's why they do it, I guess. For instance, if the jth column, these properties follow from earlier proofs. So the proof that composition of linear is linear. Yeah. All right. All right. Yeah, so let's work an example. It's worth doing that just to see that that's true. Can I do this? Maybe that's just a. Okay. Okay. And then lastly, we have 2, 3, 1, -5, and then the last column, 6 and 3, and then we're going to get 12 plus 9 is 21, then 6 minus 15 is -9. Okay, great. So then the final result is going to be 11 minus 1. Right, you could alternatively, yeah. I mean, it's all just like in different ways of interpreting the operations together. But so I'll write that down. So first call, so this is A and this is B of AB is A times B1, which is a linear com of calls of A. Every column of AB is a linear combination of the columns using weights from the corresponding column of B. Okay, so it's going to be AB is going to be um, I mean, I know it's 3 by 2, but I'm trying to think about like 3 by 5. And this is 5 by 2. Then you're gonna get combinations. Let me think. You're gonna get 2 combination of 3. Okay, so yeah, it's gonna be a 3 by 2. Okay, so they had to introduce this at some point. This is the like rule that everyone learns is like the product of a row and a column gives you an entry in the corresponding matrix. Okay, so this is the one that everyone I feel like does. So we can just move on. Okay, yeah. That's all good. All right, so now we get some theorem 2. Okay, so what we're really talking about what is the algebra of n by n matrices where the operations are plus and times? Um. Oh, but yeah. So this is okay. But what is the difference between that and this? Because this is associativity of addition. This is okay. Okay, so this is times a soak on matrices. A, B, C equals A, B, C. So that's A. B is times distribute over plus. Right and left. So what that means is, okay, C or D, we have RAB is equal to RAB. Oh, and even okay. Okay. Yeah, so the non-commutativity of matrix multiplication. That's interesting. If AB equals AC, can't cancel to get B equals C. What's an example of that? And if AB equals 0, we can't conclude A equals 0 or B equals 0. Matrix powers. Oh, all right. So if A is an n by n matrix and K is a positive integer, then we have a matrix powers. Yeah. That last one's the interesting one. AB transpose is equal to B transpose A transpose. AI. Wait, what? In order to feed a 2x2 color block in a computer, it first gets converted into a 4x1 vector. Then the computer converts the block of numbers into a vector by placing. Wait, is this? Oh, so this goes column. It's not row. It's the same though. Oh, V transpose MV. Where W is the vector generator of all white squares. It can be verified for any other vector X. If X is not V or W, then this is non-zero. Thus, if a computer checks the value, if a computer checks the value of X transpose MX and finds it non-zero, the computer knows that the pattern corresponding to X is not the checkerboard with a blue square. Wait, top left corner? Wow, this is a weird introduction. Okay. Oh, and then they check X transpose X to make sure that. Because what is. X transpose X is the same as the dot product, right? So that means that um, yeah, presumably if I'm pretty sure this is pretty basic, but if we have a vector x and dot xx is 0, then x must be the 0 vector. I'm almost positive that's true. Because otherwise you would have like a 1 times 1. Is that a footnote or a... Oh yeah, here we go. That's a good example. To see why x transpose x is 0 if and only if x is 0, you just write out the dot product as a symbolic thing, and then notice that, you know, they all got to be oh. This seems like a cool example. All right, let's get back to it. All right. The dates of ground crew incidents for February and January of 2020 are listed in the... Oh, these are just dates? There's no actual data? Oh, no. Oh, no. Each one of them represents a single incident. I get it. That's kind of okay. Scrub the data. Although the data in this example are fictitious. Okay. Okay, so here's an interesting thing. For a matrix, multiplication is parallel because the columns of B are assigned individually or in groups to different processors who independently and hence simultaneously compute the corresponding columns of. Okay. Okay. Let's do the practice problems. I never get to do this thing. Let's do this. Wait, but didn't I have a um Okay, well, we'll see. We'll see. Alright, this is gonna be a little experiment. I got the tripod, I got the cables. It's been a while since I did this, that's for sure. Okay, so I think we need to, well, just test it and then I'll take it apart and see if it works. Okay, we got this. We got this thing. Okay. So now we need to do this. And then we need to do this. Okay. And then we need to go over here. I think we need to do this. All right. Is there a bubble? How do I get it? Is it frozen? Okay, so now we're going to disconnect this. And then I need to move everything over. So the first thing we're going to do is Test? Okay. So we should be good. All right, we're rolling. All right. Now the issue is definitely, let's see, let me try this. If we go like this. Then I should be able to write on here. Wait, why is it? Oh no. Okay, I think we have it set up. I think this is gonna work. So I just need a marker. I got a marker, and then we need to come over here. Okay. Then we're gonna want to get as much over here as possible. Okay. The last thing is all right. What a setup. All right. Since vectors in Rn may be regarded as n by 1 matrices, the properties of transposes applies to in theorem 3 applies to vectors too. Okay. Oh yeah. I'm gonna have to get used to writing big. What? I have new markers. I'm gonna go get a new marker. You know what I think it is actually? It's that it's not dry. A is equal to 1 minus 3 minus 2, 4. X is equal to 5, 3. All right, we need to compute. We need to compute AX transpose. Let's see, how am I going to X transpose A transpose X transpose and then answer is A transpose X transpose defined. All right. Let's see how much of it is visible. Definitely want to do this. Yeah, I wish I had rotated it because if I was, it's a little bit harder to write like this, but this should be equal to X transpose A transpose. So these two are equivalent by the theorem, but we're going to compute them. So this is going to be equal to 5, 3, 1 minus 2 minus 3, 4. Okay, now I'm going to do it in both ways. Let's see how low we get. I want to zoom out a little bit. That seems good. Okay. So X transpose A transpose. And what we want to do is, first I'll do it as just the row column stuff. So this is going to be 5 plus minus 9. And then over here, we're going to, so this is a 1 by 2, 2 by 2. So the result is going to be 1 by 2. Okay. All right, and then the last entry is going to be a minus 10 plus 12. So this is, so the answer is minus 4, 2. I wish I could hold this under tension somehow. Because you really, when you write on it, you have to press in. But, okay, cool. So that's the first one. I'm going to go get my coffee, and then we will resume. But I got the setup, man. I got the freaking setup. Pretty cool. I should mess with the lighting, but it's so cool to see the like sun dappled. I mean, outdoor mathematics. Is there anything better? Um, okay, so the second part of this, it's the second part of this is exactly the same. So, well, actually, you know what? I guess I did this wrong. This is the second one. The first one is going to be so let's just erase this. So this one was minus 4, 2. So the next one we're going to have, let's just compute AX. So we have, yeah, let's see. I wish, we're going to have to refine this system. But we have 1, 1, minus 3, minus 2, 4, and 5, 3. So this is going to be equal to, we'll do it as the linear combination this time, just to vary it. So this is going to be 1 minus 2 plus 3 times minus 3, 4. So we're going to get 5 minus 10 plus minus 9, 12. And we get the exact same as before. 4 minus 4, 2. Okay, so we just verified that AX transpose is, oh, and then, oh yeah, because see this, this is a column. So this is minus 4, 2. But then transpose is equal to the 1 by 2 minus 4, 2. Is that visible? Am I standing in front of it? Let me see. It might just be... Okay. So we verified those first two. Okay, now we need to do x transpose. X transpose is going to be 5, 3, 5, 3. So this is a 2 by 1 by 1 by 2. So the way we're going to do this is we could think of it like this. It's going to be 5, 3, just times 5, which is going to be 25, 15. Then concatenated horizontally with a 3. So I believe this is going to be equal to 25, 15, 15, 9. So the other way we could do this is it's going to be 5 times 5. So, okay. So that's the way to write it as a linear combination of columns. The other way we could do it is 5, 3, 5, 3, where the result is going to be this row times this column, this row times this column. So here, here, 15, then here, here, 15, and then finally here, here, 9. So that's the two ways of computing that. We're done with that. You got to move on. So is A transpose X transpose defined? The first thing we could do is A transpose is 2 by 2, and X transpose is 1 by 2. So A transpose X transpose is not defined. All right, cool. We're getting in the flow. That's the first practice problem. Let's just check our answer. We get it right. Minus 4, 2. Yep. Oh, you know what we didn't do, though? We didn't do X transpose X. Forgot that one. So that one is, so X was equal to 5, 3. So we're going to have 5, 3, 5, 3. So here's what we're going to do. It's going to be 5 times 5 plus 3 times 3 is equal to 25 plus 9 equal to 34. That's the last one. That's the dot product of X with itself. All right, let's do the second problem. So I wonder if I can, maybe to introduce the problem, I will scene switch. So the second practice problem is let A be a 4x4 matrix and X be a vector in R4. What is the fastest way to compute A squared X? So let's think about the number of multiplications there. Okay, so A is a 4x4 and X is R is 4. So computing A's, what the hell is happening? A squared X. What the hell? Computing A squared X. Let's just do it with a 2x2 and a 2. Why do we need to do, actually, you know what? It might, 2 might not work. Maybe 3. Anyways, the point is it's A squared X is equal to X. So the question is whether or not it's faster to compute A squared before you multiply it or after. So computing A squared so we're going to have is that in the shot? That is in the shot. It's just so small. I don't think any, let me look at it on my phone. I think there's no way that anyone would be able to see that. Yeah, I think next time I'm going to flip where the camera's at and where I'm at. Because I have the angles. I just don't have the, I need to be able to write it like this with the camera to my right. Anyways, here we're going to get, just for the first element, A times A plus B times B plus C times C. So this is 3 for, so it's going to be, if we just like put a matrix of the number of multiplications, it'd be 3, 3, 3. So it's going to be, if A is n by n, then I believe the number of multiplications is n, to be n squared times n. It's going to be n cubed. Does that make sense? Because you're going to have n squared times n, and if let's try it if it was a b. A is n m by n. B is n by m. So then we're going, so this is the number of rows. So for each dot product, we're going to have, so for each row, we're going to have mn multiplications, then times, so this is the number of n, so the result AB is m by m. So the way to think about it is that then we're going to have m by m, where the number of dot product multiplications we need is n. So we're going to get times m. This is going to be m squared n. Okay, cool. So that's the scaling for the number of multiplications in a matrix multiplication. Okay, so now what we want to consider. Okay, so a squared requires n cubed number of multiplications. Now we want to consider how many does it take for ax. So ax is this top case, and we're going to have, it looks like it's going to be 3, 3, 3, right? So it still looks like it's n squared. So then if we were to, so ax requires n squared. So then ax is going to require n 2n squared. Because it's going to be n squared. Or is it this? I think it's that. So I think what you want to do is you want to compute a squared first. So let's figure that out. So the answer in the actual textbook is so wait, let me so I got it wrong. They're saying ax requires 16 multiplications. So if x was in R4, and well, let's just do R3 because it doesn't really matter. So we should need 9 multiplications for ax. So we're going to need, it's not squared. It's not squared. Because it's going to be n squared plus n squared. Yeah, so this is 2n squared. So this is going to be equal to 18. Okay? But for doing the matrix multiplication first, we're going to get 27. So yeah. And that scaling checks out because if it was 4, we'll do the case if it's 4. It's going to be 4 cubed versus 2 times 4 squared. So this is 32 versus 64. Oh, but you know what? I got this wrong. It's so n cubed is the number of multiplication just for a squared. But then you still need to compute a squared x. So you have n cubed plus n squared, which is equal to 80. Okay, yeah, so it's actually way worse to compute a squared before you multiply it by the vector. That's kind of weird, man. That was a good problem. That was a good problem for sure. I like that one. All right, the third problem, we'll switch over. Suppose A is an m by n matrix, all of whose rows are identical, all of whose columns are identical. Okay, so is my mic working? Okay. So here's what we have. We have A is m by n, B is n by p, and we can think of A as equaling like row 1, row 1, row 1, because it's all copies. All of the rows are identical. And B has columns B1, 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 and this is going to be P columns, N rows. This is going to be M rows, N columns. So if we think about the product AB, so the first thing to notice is that R1, B1, if we do, let's see, A, B, C, D, E, F, G, H. If we, this is just a 2 by 2 by 2 by 2. If we, so this top quantity here is going to be AE plus BG. So this is going to be equal to a matrix whose every element is identical. So it's going to be a matrix. So the way to write this, I guess, would be that AB, let's just say equals X. Then it's going to be X, 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 for whatever. MP. So basically it's if all the rows of A are identical and all the columns of B are identical, then all of the entries of A times B are going to be exactly the same. And let's just check the answer. Yeah. Okay, so we were right. Okay, so that's it for the practice problems. Let's just look at some of the problems and see if we can find a good one. Okay, so 1 and 2 are shape checking. I don't really care about that. All right, let's just do it in our heads. Minus 2a, that's fine. You just compute it. B minus 2a, that's also fine. A times C, this is a 2 by 3. That's not defined. AC is not defined. CD, however, is defined. And then A plus 2B, that's good. 3C minus E, that's not going to work. C times B, 2 by 2 times 2 by 3, that's going to work, and its shape is going to be 2 by 3. And then EB, 2 by 1 by 2 by, yeah, that's not going to work. Okay, so we just did that. We didn't actually compute it, but, we verified the shapes. Now we're on 3 and 4. In the rest of this exercise, you should assume that each matrix expression is defined. Three times the identity minus A. Let's look at that. So if we just had 2, 2, 0, 0, and then we had A, B, C, D, it's gonna be equal to 2A, 2B, yeah, 2C, wait. Yeah, 2C, 2D. Okay, so for that one with the identity 3IA, it's the same as just multiplying. Yeah, so 3IA is equal to 3A. You really don't need the I. and then 3i2 minus a. A is 4 minus 1, 5, and minus 2. So we have 3, 3, 0, 0, plus minus 4, minus 5, 1, 2. This can be equal to minus 1, 1, minus 5, 5. All right, so we did it. And then okay. Cool. Let's see. All right, let's go back to the exercises. So they said for this one, it said compute A, B in two ways. One where you treat each column of B as a vector, and then you just do sort of standard linear combination of the columns of A, and the other one is just a row column rule. I think we could skip those two. If a matrix A is 5 by 3 and the product is 5 by 7, then B is going to be the size 3 by 7. How many rows does B have if B times C is 3 by 4? It's going to have 3 rows. Let A equal this, B equal that. What values of K will make... Oh, that seems fun. All right, we're going to do number 9. So number 9 is... So let's just write out A and B. A is equal to 3, 4, minus 2, and 1. B is equal to 5, minus 6, 3, and K. Which K cause AB equal to BA? I'll be right back. Okay, so what I think I'm going to do is a hybrid thing. I'm going to go to this, and then we're just going to use this. Okay, so while I'm waiting, so A is 3, 4 minus 2, 1. B is equal to, and then we have to do this, at variables K. B is 5 minus 6, 3, and K. So now we're going to compute A times B. And D is equal to B times A. Okay, so now we can, so now we should be able to do a C minus D, right? C minus D. And then basically if these two things are 0, what the hell's going on? So if these two things are 0, K must be equal to minus 8. So the solution to this problem is compute AB and BA. Then AB minus BA. We get, what were the values? We get a matrix 0, minus 32 plus 4K, and minus 16 plus 2K, and 0. So we find just by solving this that K equals 8. So that's the value that that causes AB to equal BA. All right, let's keep looking at problems. So the number 10 looks kind of interesting. Yeah, 10 is pretty interesting. Cuz it's like why? is it the case that if we had um, if am I on the right scene? If I have a matrix and two vectors which are different, is it possible that the matrix vector multiplication of both of them is equal? I think no, unless it's zero. Yeah, if the matrix is non-zero and yeah. Oh yeah, well that's okay, but if it has full rank, full rank isn't unless you specify which. Okay, yeah. So I was assuming square. Yeah. So okay, cool. So we're building up to all this injectivity stuff. Okay. Okay. So first thing to notice though, that the columns of A are not linearly independent. If you multiply the first column by -2, you get the second column. Um, so is this okay? And for matrix multiplication, is this also true? Wait, why isn't it doing it? If we're considering the multiplication of matrices, if like let's say AB, then if A is invertible, square full rank, then if there's another matrix C and A times C is equal to A times B, then if A is invertible, then C and B must be equal. Okay, yeah. So you're only going to get this case when there's basically some lameness in A. All right. Number 11, compute AD and DA. Explain how the columns or rows of A change. Okay, number 11 looks pretty good. So D is diagonal and A is non-invertible. Okay. I might do a simpler version of that problem, but that's a good one. Okay. So DA is going to is a scaling operation along the three different axes. But AD, so explain how the columns or rows of A change when A is multiplied by D. On the right or on the left. So for DA, A gets its rows scaled by 2, 3, and 5. Now for AD, so let's do AD. So AD is going to be A, B, C, D. And the thing is, this is general, but A in the original problem is linearly dependent in its columns. Okay. So this is going to be wait. A times 1, B plus 0, 2B, 2B, C. Okay, all right, interesting. And so in the other case, of AD, A's columns are scaled by diagonal. Wait, actually, I think this is wrong. So wait, this one is equal to so then this times xy is going to be equal to ax plus by. Hmm. Oh yeah. Okay. I'm just trying to get a sense of like what the thing does. Okay, so I think we answered the first part of the question, which is explain how the columns or rows of A change when A is multiplied by D on the left or the right. Basically, if A is multiplied by D where D is on the left, then A's rows are scaled. But if A is on the left, then A's columns are scaled. All right, so the last thing is we actually want to write out A. A is equal to 1, 1, 1, 1, 2, 4, and then this should be 1, 3, 5. And I'm pretty sure that is it invertible? I can't tell if it's invertible. So if we look at, all right, so let's just do this. A is equal to 1, 1, 1, 1, 2, 3, 1, 4, 5. We call the RF of A. Oh, it is, okay. So wait. Find a matrix B such that AB. I'm pretty sure that that has to be the inverse. I'm almost positive. So if we do in A, I don't know how they expect us to find the inverse, though. I think maybe we should try it with a 2 by 2. The 3 by 3 is too much. 3 by 3 is going to be too hard. So if we just consider this, we want to find b not equal to 0 or I such that AB equals BA. So AB minus BA is equal to 0. Okay, so let's just do this. 1, 1, 1, 2 times A, B, C, D. We get is equal to, so this is going to be AB. Because B is just totally unknown. So this is going to be A plus C, B plus D, A plus 2C, B plus 2D. And then A, B, C, D times 1, 1, 1, 2. This is going to be scaling its column. I believe that this is going to be equal to A plus C wait. Did I do this wrong? A plus B, A plus 2B, C plus D. Is that right? Did I do that right? A plus B, A plus 2B, C plus D, C plus 2D. Okay, so now what we want to do is find, this is going to be AB minus BA. So this is going to be A plus C minus A plus B. So this is going to be C minus B. And this entry is going to be B plus D minus A plus 2B, which is going to be minus A, let's do D minus A minus B. Then this problem is kind of cool, actually. Okay, so let's just keep going. So we get A plus 2C minus C plus D. So we're going to get A plus C minus D. And then here we're going to get B plus 2D minus C plus 2D. This is going to be equal to B minus C. So this has to be equal to 0. So C, okay, so let's do this. C minus B plus C is equal to 0. A plus C minus D is equal to 0. Minus A minus B plus D is equal to 0. And finally, B minus C is equal to 0. So if we are to turn that into a matrix and solve it, then we should get all right, let's leave that up. So we're going to get a matrix that's 0, minus 1, 1, 0. Then I guess we could do the augmented. Then this is going to be 1, 0, 1, minus 1. This is going to be minus 1, minus 1, 0, 1. 0, 1, minus 1. So if we just plug that in and all right, let's just try to reduce row echelon format. I don't know what this is going to do. This might be totally foolish. 0, minus 1, 1, 0, 0. 1, 0, 1, minus 1, 0. Minus 1, minus 1, 0, 1, 0. And 0, 1, minus 1, 0, 0. So A plus C. Damn, I wish we had an answer for this one. Well, actually, you know what? Let's see. So we end up with this has got to be redundant, right? B equals basically is what this is. Yeah, minus B plus C equals 0. So then B equals C. That's the same as this equation. I don't know if I messed that up. But then A plus C equals D. And this says minus A minus B equals minus D. So A plus, wait. Oh, I shouldn't have erased all that. The answer is the inverse. I just don't know how they want me to compute it now. All right, let's try to do this symbolically, I think. So if we had, all right, so let's just do variables A, B, C, D. Then we, oh my gosh, that's so annoying. Okay, then we did A is equal to 1, 1, 1, 2, right? We're just taking the first two rows and columns. Then we did B is equal to A, B, C, D. Now A times B minus B times A. So we get this system of equations, and we want to make them all 0, right? Let's just plug in 1 for B. So if B equals 1, then we get C is equal to minus 1. So then we get minus A minus 1 plus D equals 0. And we get A minus 1 minus D equals 0. So then we get D minus 1 equals A, and A minus 1 equals D. Is that possible? It seems impossible, right? Okay, I'm calling in the big dogs. I'm asking for help. Right multiplying scales the columns, yeah. Left multiplying scales the rows. Oh, I'm so silly. Any other non-zero polynomial? Wait, let's just try that. So if we had a, this is obviously gonna be I. So inverses commute. Yeah. That's actually pretty cool that inverses commute like that. Did it require that A is not equal to B? Or B is not equal to A, I mean? Yeah, you just take A. Oh, I'm so silly, man. Like, I always miss the obvious answer. Okay, that was a good problem. Let's keep going. If the columns of A are linearly independent, then I think the null space is only the zero vector. So it only has the trivial solution. Okay, so let's try to do number 12 then.
Okay, I think I figured it out. Okay, so what we have here is A is this, B is just symbolic 2 by 2. And what we're trying to find is that AB, so find AB equal to 0. So this is going to be the first column. And the second column is going to be so B is going to be equal to, oh wait, if B equals what, 1 4 1 4, then we're going to get oh wait, sorry. I think it's going to be 4 4 that. So yeah, so we're going to get 8 minus 4. Wait, hold on. Did I mess this up? Let's check it on a calculator. Okay, so A is equal to 2 minus 8 minus 1, 4. B is equal to 4 4 1 1. A times B. B times A. Or no, yeah, of course. Okay, great. So we did it. Use 2 different non-zero columns for. Oh. Wait, can't we just do 8 and 2? I think we can just do 8 and 2. So okay, cool. Yeah. So they just need to be a scalar multiple of each other. Let R1 to Rp be vectors in Rn. Let Q be an M by N matrix. Wow, we're really starting to amp up the because before it was all about computing and computing RFs and all that easy stuff. Now it's getting a little bit cooler. Okay. Wait, this one's easy. This is going to be an n by p. So it's just going to be q times big R. That one's easy. I don't want to go back to section 1.8. All right, true, false. True, false are actually really good. I love true, false. If A and B are 2 by 2, 15 is false. And it's false because, first off, A1, B1 doesn't even make sense. Because that's going to be a column times a column. So those shapes don't even make sense. If A and B are 3 by 3, this is also wrong. It's not a sum. Because then you would get a single column. You'd get a 3 by 1. What you want is a 3 by 3. Okay, so this is false. Each column of AB, each column of A times B is a linear combination of the columns of B using weights from the corresponding column of A. That's also false, I believe. I'm almost... Yes, it's a linear combination of the columns of A using weights from B. So they flipped it around. All right, number 18. The second row of A times B. So what are the rows in matrix multiplication? So the row is going to be the like nth row of A dotted with all calls of B. So what is it? So let's see. 18. The second row of AB is the second row. Yeah, that's actually true. Okay, I believe 18 is true. All right. Now A times B plus A times C. That is true, but I don't know why. I know that it's in the theorem. that matrix multiplication distributes over addition. But I don't have a good intuition for why. The 20? That should be true. I don't see why that wouldn't be true. Okay, so let me just write all these down so that we can check them later. So 15 false, 16 false, 17 false, 18 true, 19 true, 20 true, false. 21 is definitely false. 22 false. The transpose of a product of matrices, that's false. It's a reverse order. 24, the transpose of a sum of matrices equals the sum of their transposes. Yeah, that's true. We just did that one. Oh, we're done with the true falses. Okay. All right, I'm gonna take like a 5-10 minute break. I'm gonna walk around the block or something. Okay, I'm back. What are we doing? Let's read through some of these. If the first two columns of B are equal, then the first two columns of AB are going to be equal because the linear combinations are going to be the same. Similarly, the row column products are also going to be the same. All right. Well, okay, I want to do 27. Let's do 27. Okay. On the board. Let's get it. Okay, so the question was if B looks like this, we have A, B, C, D, and the third column looks like A plus B, C plus D. Then the idea is that A, B is going to look like this. A, B1, A, B2. Might be hard to see, but whatever. And then A, B3. But A, B3 is equal to AB is equal to A times B1 plus B2 is equal to AB1 plus AB2. So the point is that the third column of the resulting the third column of the resulting matrix is going to be linearly dependent. No way around that. So that's the answer to that one. All right, moving on. So 27 is done. 28. Suppose the second column of B is all zeros. Well, that's got to be 0. All right, suppose the last column of AB is all zeros, but B itself has no columns. No. That one's interesting. So, AB, okay, 30 we just showed, but let's do number 29. The last column is all zeros. So let's say we have some A times X is equal to 0, but X is not equal to 0. So that means that's the thing about linear algebra. There's so many theorems to remember. But yeah, so we have like, for some A, we have like A times X is equal to 0, but X is not equal to 0. So then, one immediate thing is this must mean that the columns of A are linearly dependent because there's a free variable. I think that's true. I'm going to look up the answer to that one, but I'm almost positive that that's the conclusion they want us to have. Nice. The columns of A are linearly dependent. Non-trivial null space. That's exactly what we said. Okay, so 30. If B are linearly independent, then so are the columns of A. And the way that you can, well, actually, maybe that one deserves a little attention. So what did we just say? If you have a column that's like dependent, so B1 plus B2, and you apply A to it. So if we said B3 as a column is equal to B1 plus B2, and then we wanted A of B3 is equal to A of B1 plus B2 is equal to A of... So what does it mean for the columns of... Yes, okay. So maybe this will show it. Might as well. So let's say that we have B is equal to a bunch of columns, B1, B2, and B3, and excuse me, and B3 is a linear combination of B1 and B2. It's just the sum. Then if we want to compute what A does to that column, then we can substitute B3 for its definition, and then we can use the property of linearity of linear transformation to get AB1 plus AB2, but we know that this is dependent because AB1 is the first column of the resulting AB. So AB is going to be equal to AB1, AB2, and AB3. So that's that. All right, so we did that one. Okay. 31. Suppose CA is equal to the identity matrix. Show that the equation AX equals 0 only has the trivial solution. Um, okay. So we know that CA is equal to IN. So if C is N by P, A is P by N, then the resulting is going to be N by N. So it's equal to N by N. Now what we want to know is show AX equals 0 only for X equals 0. All right, this one's a good one. We also want to show A can't have more rows than columns. Which would mean P is less than or equal to N. Am I on the right? Okay. So let's think about this. Okay, so wait, hold on. If we did CAX is equal to, I think you can do this, right? INX. this is going to be equal to x. So I mean, I is independent. And since I is independent, then it spans Rn. And since it spans Rn, it only has okay. So I only has the trivial solution. If x was not equal to 0 and ax, let's say, equals y, then cy is equal to ix, which is going to be equal to x. Cy but this is 0. Yeah, this has to be 0 because we said that ax is we assumed, yeah, assume x is not equal to 0. Then but ax is equal to 0. So it's a non-trivial solution. We assume x is a non-trivial solution of ax equal to 0. Then we substitute it in and we get, for y, we get cy is equal to ix because we multiply both sides by x. And then but this is since y is a non-trivial solution to ax equals 0, then y is 0. So cy has to be 0, but then x is equal to 0, but we assume, so then it's a contradiction. All right, so that's that. So we just did the first part, but now we want to show why A can't have more rows than columns. I forgot some of the theorems about the row count. If there's more rows than columns, if p is greater than n, then A doesn't span R. Doesn't span RP. So yeah, that's what it is. So it doesn't. So if p is greater than n, then um, yeah. So it's not going to span RP. And if it doesn't span RP, right, because also because the linear combination. This one's actually tripping me up because I feel like you can have something with more rows than columns, but then still have, like, let's see, like if A was like one, uh, so this is C and this is A. Okay, I'm gonna ask because I don't get this problem. I feel like I just constructed an example that proves that wrong. Oh wait. Oh, I misread it. I misread it. It's the other way around. Okay, wait, hold on. Let's go back. So if n is greater than p, let's erase all this crap. If n greater than p, then 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 A has more variables than equations. So free vars. Which means, what about the pivots? Um, um, wait, is this linearly dependent? You don't need a non-trivial combination of the other vectors to produce the zero vector. You only need a non-trivial combination of all the vectors that equals 0. Okay, all right. So yes, so free vars and calls of A are dependent. But how does that help us show that? I mean, I'm almost positive the punchline is that oh wait, well, the columns of A are dependent. Okay, wait. So then CA is gonna be equal to C A1 to CAN. But since AN is the zero vector, then we're gonna have a zero. We will get a zero column, but then CA is not equal to IN because IN is independent. All right, that's my solution. Let's see what their solution is. Or let's see what ChatGPT answers this thing. I don't know why this shows that at all. Okay, I don't know. Just keep going. Hey, more water. Yeah, the thing about linear algebra is that there's so many different ways to say the same thing. Okay. Okay, we'll do 35. Why not? Okay, so this is inner. This is also inner. And I expect these to be this. I expect these to be equal, and so do these. So this is going to be outer and outer. All right, so UTV is going to be equal to -2, 3, 4, A, B, C. It's going to be equal to -2A plus 3B plus 4C. Now, VTU is going to be equal to ABC times -2, 3, and 4. This is going to be equal to, let's see, how's this looking? Not too bad. So this is going to be equal to -2A plus 3B plus 4C. All right, so we are correct. Those are equal. So the inner product of any two vectors is, for any two vectors, their inner product is commutative, meaning you can, I don't know if that's exactly the right way to say that, but they're equal. Now, wait, I wrote this wrong. UVT and VUT. So we're going to get this is going to be a All right, so that's pretty interesting, actually. Uh, so UVT is equal to U T T. So the outer product, you have to transpose it to get the actual same thing back. Oh, and that's number 36. So 36 is how are they related? And we just answered that. If for the inner products, it's the same, and for the outer products, it's their transpose is the same. Okay, we have to do a proof. Okay, so let me. So, prove theorem 2b and 2c. Let's see, how many left do we have? Because it's already 1 p.m. and I need to get going. We should do one of these. Okay. All right, so we're going to prove. Oops. All right. Prove 2b and 2c. All right. Okay. So now, wait, let me get the statement of the theorem. Theorem 2 is, so theorem 2b, so theorem 2b is that AB plus C is equal to AB plus AC. So this is equal to sum AB plus AC with all the indices working out. Okay, which is going to be, which should be equal to the sum AB plus sum AC, which is equal to AB plus AC. Okay, that's the proof of that one. Now the next one is 2C is that B plus CA is equal to BA plus CA. So to prove this, Dij is going to be equal to the sum of B plus C times A, which is equal to sum of BA plus sum CA, which is equal to BA plus CA. Okay. Pretty simple, actually. I thought it was going to be harder than that. All right, what's the next problem? Okay, so we just did prove this theorem. Oh, what's theorem? You're probably going to get like a term like R. Yeah, I don't think we need to do that one. Show, okay, 39. Show that .41 seems kind of cool. 41 seems kind of cool because I think we're gonna ask ChatGPT, but I'm pretty sure that for problem 42, which says give a formula for ABX transpose. So this is going to be, let's see, this is going to be n by m. This is going to be p by n, and this is going to be p. So then we get a 1 by, and this is n by, this is m by 1. Is that true? This is m by 1 because we get an. Yeah, I'm pretty sure that we got it right, but let's double check. All right, cool. We got it right. Good stuff. Good stuff. They have all these applied problems in here. I like the applied problems, actually. Let's just read them, though. Okay, so the first one was use a search engine to find documentation for a programming language to be able to generate ones, zeros, diagonals. Anyways, I know how to do all that. A useful way to test new ideas in matrix algebra, make conjectures, make calculations with matrices looked at random. Checking a property with a few matrices does not prove that the property holds in general, but it makes the property more believable. If the property is actually false, you may discover it when you make a few calculations. Okay. Ooh. That one seems fun. 45 we might do. I think that's going to be it. Let's see, how long did it take to do one section? 4 hours? Yeah, see, it's like double what it normally takes. Okay, well, we'll try to... I'm going to do the homework for this section. And then we'll get into the inverse of a matrix. All right, cool. I feel like this was pretty successful.